I would just like to say for the record that I explained number 14 beautifully and I was not recording. So if you're ever making a video, especially for school, make sure that you are recording before you begin speaking. Yes, so just talk to myself for a good 10 minutes or so. So the purpose of this video is to talk about homework question number 14, which we did not get to in class today. We ran out of time. 14 and 15 are on the bottom of the third page of homework from the first set of homework from Work and Energy. You cannot do the three questions above 14 and 15. You can only do 14 and 15. So 14 is a special application of basically conservation of energy. It involves picturing the situation and taking into consideration what you already know about forces. Okay, so 14 was meant to be a little bit of a challenge, and we're going to talk about it right now. So in 14, we have a spring that stretches by 21 centimeters when a 135 Newton object is attached to the spring. So physically, what's happening here? We'll pretend that this is the ceiling. Okay, and attached to the ceiling is a spring. We add a 135 Newton object to the spring. Okay, so when you're given information about an object in kilograms, that's the mass. If you're given the description of physically of an object in newtons, that's the weight of the object or the force of gravity. So we're told that the weight of the object is 135 newtons. And when that force is added to the spring, when that weight's added to the spring, it stretches by 0.21 meters. Okay, X needs to be in meters. So on this spring, we add our object. And when we add the object, our spring is going to stretch from its equilibrium position, its resting position. It's going to stretch the distance X is equal to 0.21 meters. Okay, so what the heck does weight have to do with elastic potential energy? Let's take a look at a free body diagram for this object in question. So if we focus here on our mass, our weight that's added to the spring. If we come back over here, I'm going to draw an FBD, free body diagram, for the weight added to the spring. It could be a hanging mass, it could be a fish, okay, whatever the object is, we'll call it a mass initially. We want to consider what forces are acting on this object. So, hopefully you're thinking, right, the force we can never escape is the downward pull of gravity. So we have Earth's gravitational pull on the hanging mass here, which we're told is 135 newtons. What's holding it up? What's balancing out that force of gravity, that downward pull? Okay, if you look in my little window here, right, when the spring's at equilibrium and we add a mass, it'll stretch and reach its new equilibrium length, where it's technically stationary. So all the forces should be balanced. What's holding the mass up is this spring. Okay, in our last unit when we had a cable or a string, S-T-R-I-N-G, I know I say those very similar. The string, we call that a tension force. When it's a spring, Okay, that's the spring force. So the spring is what's holding the object up. So the force that's opposing the force of gravity would be the spring force. If the system's in equilibrium, these two should be equal to each other, right? The sum of the forces in the y direction should be 0. So what this proves here is that the force of gravity, the weight of the object, is equal to the spring force, meaning the force that stretches the spring. The reason this works, right, this relationship, weight is the spring force when it's a vertical spring mass system, because that weight is what causes the spring to stretch. If we were talking about a horizontal spring mass system, which are the types of systems that we've been looking at in class, that is not true, right? A free body diagram of this object, we'd have the force of gravity straight down. We'd have the normal force balancing out the force of gravity. So the table or the surface below would balance out the weight, not the spring force. The spring force, if we were stretched a distance x from equilibrium in the positive direction, right? Our spring force would be pointing in the negative direction, opposite to the stretch. Okay, so in this case, the spring force is not equal to the force of gravity if it's a horizontal spring mass system. That is only true in a vertical spring mass system because the weight is what causes the stretch. So with that in mind, if we know the spring force that causes that stretch, F sub s, is 135 newtons, and that force causes the spring to stretch 0.21 meters, we can use that information to find out the rigidness of the spring, which we're not told in the problem, and we need for part 2. So we consult Hooke's law, which states that the load applied to the spring is proportional to the stretch distance of the spring times the rigidness or the spring constant of the spring. So we know that the spring force is 135 newtons. K, we don't know, so we leave that as a variable. And the stretch distance is 0.21 meters. So we divide both sides of the equation by the stretch distance, and we get 642.9 newtons per meter. So this basically describes that this spring requires 642.9 newtons to stretch it 1 meter. So that's a measurement of its rigidness, how difficult it is to stretch the spring. Okay, K can vary drastically. It can be anywhere from 10 to, realistically, I've seen 20,000 on an AP exam. So it really does have a big range. It depends on the system, right? A pen spring is going to have a lot less, a lot smaller K value than the spring that we use in a car, right? So K can vary drastically. Now that we know the spring constant of the spring, the second statement here says, what is the weight of a fish that would stretch the spring by 0.31 meters? Okay, so physically in this situation, you don't have to draw this, but just to help us visualize, we have this same spring. So the spring constant will not change. When we add this new weight onto it, it's going to now stretch a new displacement of 0.31 meters. The spring itself has not changed. The material has not changed. So K will not change. K will be constant. We can figure out the weight of the fish, meaning the restoring force. I keep calling it the restoring force. The spring force. Okay, another name for F sub s is the restoring force. We get to that a little bit later with harmonics. But if we have this new stretch distance and the spring constant K, we can figure out what force is required to cause that stretch using Hooke's law. So we're looking for the new force or the weight of the object. They're equal to each other in a vertical spring mass system. I'll take 642.9 newtons per meter and multiply by 0.3 meters. 0.31 meters. And we get 199.3. Our units here, our meters will cancel. We're left with just newtons. So our answer to 14 will be A. The fish must weigh 199.3 newtons to cause 0.13 meters of stretch. Okay, 15 is more similar to the examples that we looked at in class. I hope that helped, and I will talk to you guys on Friday. Have a good rest of your day.